Okay, so this lecture is going to be about the Gershgorin circle theorem. Okay, so in the previous lectures, in this segment, we have come across a lot of scenarios where it's very important to either find the eigenvalues of a matrix or some property that is related to the eigenvalues of a matrix, right? For example, we encountered some situations where it's very useful to have some idea about the spectral radius of a matrix, right? If the spectral radius is less than 1, then, matrix powers will keep going to 0. And, the smaller the spectral radius is, the faster they go to 0, right? So it's of interest for us to know. We saw in gradient descent, if you look at the assignment, well, primarily what comes in is the spectral radius of some matrix, right? Then you can also it's also of interest to check whether a matrix is positive definite or not, right? It's very useful in applications where you're concerned with minimizing quadratic functions, right? If the corresponding matrix that's forming the quadratic part is positive definite, then it has a unique minimum, right? The quadratic function has a unique minimum. So it's interesting to know whether the matrix is positive definite or not. In both these scenarios, you don't need to know the full eigenvalues, right? You only need to know some property, some consequence of the values. Okay. Well, you know that to find the eigenvalues, if A is, let's say, n cross n symmetric, or let's say A is n cross n matrix, right? Order n cube operations are required to find the eigenvalues, roughly speaking, right? Order n cube operations are required, but that gives you all the eigenvalues, right? That may not be very efficient here because I don't need to know all the eigenvalues exactly. I just need some property, right? Also, oftentimes I may not know the matrix A exactly, right? I may only know some structure of the matrix A. Okay. We'll look at some examples later in this lecture. Maybe I know, for example, that the rows of A all sum to 1, right? And I know that the entries of A are all between 0 and 1. And the rows sum to 1. That's the only information I have about A. I don't know the entries of A, right? In that context, I can't apply an algorithm to get the, because I don't even know the values, right? I don't even know the values of the matrix, right? So in that scenario, how can you conclude something about, the spectral radius or, the definiteness of the matrix? Okay, so these are very useful problems to think about. So we need a very quick and a very simple way to check, right? Roughly give some information about the eigenvalues of a matrix. Okay, that's what the circle theorem hopes to do. Okay, I'll explain the theorem in a minute, but first there are some matrices for which these answers are very obvious, right? And that would be the diagonal matrices, right? If a matrix is diagonal, so let's say I have a matrix with diagonal entries like 10, 2 and 1, just arbitrary numbers I put in, right? Immediately I know that the eigenvalues are 10, 2 and 1. Immediately I can see the spectral radius is 10 and the matrix is positive definite. I can answer all these questions immediately for diagonal matrices, right? Diagonal matrices are nice for us, right? And that's where the spectral theorem, for example, derives its strength from. Spectral theorem says every symmetric matrix acts like a diagonal matrix in some rotated coordinate space, right? Or something to that effect. So basically, diagonal matrices are very nice for us, right? Now consider the following, simple perturbation, meaning suppose instead the matrix being diagonal, it is still, the diagonal entries are 10 to 1, but the off diagonal entries are non-zero. However, they are very, very small. So this is like 0.1 maybe, like 0.1, this is 0.001, this is 0.2, this is 0.001, and this is 10 to the minus 5 or whatever, right? Just again arbitrary numbers, right? In this case, the matrix is not diagonal, right? But what do we expect, right? Well, we expect here from basic intuition that the eigenvalues of this matrix must actually be close to 10 and 2 and 1, right? Maybe even this matrix has 3 eigenvalues, distinct eigenvalues, one of which is close to 10, the other one is close to 2, the last one is close to 1. That's what our intuition tells us, right? The Gershgorin circle theorem makes this a lot more precise. Okay, so that's the point of this theorem going to be. It will make this precise. This intuition is going to make precise. So it's what circle theorem is going to do is, it's going to tell you that all the eigenvalues will be around the diagonal entries, but within some perturbation, within some radius. Okay, That's where the word circles are coming from. Okay, so without any further delay, let me go ahead and define the circles and lay the groundwork for the circle theorem. Okay, so where are the circles coming from? Okay. So just like in the scenario when we discuss spectral radius, here we do not limit ourselves to symmetric matrices, right? For us, a matrix A is going to be an arbitrary square matrix. We're only looking at square matrices because we're dealing with eigenvalues here, right? N cross n square matrices. Okay, so it may be symmetric, it may not be. I don't really care about that. Okay, in that case, the eigenvalues are potentially complex numbers. So eigenvalues are potentially also have an imaginary part. Right? Eigenvalues may have both real and imaginary part. Correct. So we all know how to find the eigenvalues, right? This is the definition, right? So Ax equal to lambda x. If I am able to find a vector x, a non-zero vector x to be precise, such that Ax equal to lambda x, then lambda is the corresponding eigenvalue. Okay, that is what we know. That's the definition, right? How do you find eigenvalues? Well, algorithmically you actually have to do the spectral decomposition, but formulaically you can also approach it by constructing the characteristic polynomial. So the det of lambda I minus a, you construct this polynomial and you find the roots of this polynomial. Right? So in general, this any polynomial in general could have complex, could have roots with imaginary parts, right? So we have to deal with complex roots here. Okay, so the eigenvalues in general will be on the complex plane. Okay, that's why we talk of circles and radii, just like when we define the spectral radius, right? Okay, fine. So this is the complex plane we're going to deal with, right? Okay, so what I'm going to do is I'm going to construct circles in the complex plane. Okay, so starting from the matrix A, which is n cross n, I'm going to construct n circles. Okay, the n here is basically the n cross n here, this n. Okay, so I'm going to construct n circles, one for each row of it. Okay, how to construct in a minute, one for each row of it. Okay, so for row 1, I'll construct circle 1 by taking center to be the diagonal entry A11. Okay, and radius to be, okay, so this will be the center. Radius I'll define in a minute. So basically, for the first circle, the center will be the first diagonal entry A1. Okay, for second circle, circle 2, the center will be A22. Okay, radius I'll define in a minute. Let's call it R2. Okay, so in general for row I, the center will be AII and radius will be RI. Okay, and what is this RI? Okay, so basically I'll construct n circles. Okay, the centers of the circles are the diagonal entries of the matrix. Okay, and the radius essentially represents how far the eigenvalue goes. Okay, that's going to be the statement of the theorem in a minute. Okay, so Ri is going to be basically the sum of all the off diagonal entries. Okay, so what are the off diagonal entries? So Aij will be off diagonal entry in row I, where j runs from 1 to n. So j is the column index. J runs from 1 to n except I, because we want the off diagonal entries, okay, excluding the diagonal. So basically we're going to sum this, but we're going to sum with an absolute value. Okay, so it's a sum of the absolute values of the off diagonal entries, right? So j not equal to I, so that is going to be Ri, that is going to be the radius of the ith circle. Okay, so this is how you construct the n Gershgorin circles. Okay, the radius of the ith circle is the ith diagonal entry AII. The center of the ith circle is the ith diagonal entry AII, and the radius of the ith circle is the sum of the absolute values of all the off diagonal entries. Okay, then what does the circle theorem say? Okay, the Gershgorin circle theorem says that any eigenvalue of A lies in one of the Gershgorin circles. Okay, so basically you draw these circles in the complex plane. Okay, what it says is that any eigenvalue A you pick, it will be in one of these circles. Okay, So essentially, if you take any point outside all these circles, that cannot be an eigenvalue. Okay, so let's take an example to see what they mean. So let's take a very simple 2 cross 2 case. So A is equal to, let us say, 1, 1, minus 1, 2. Again, arbitrary values I have filled up. Let us see how this goes, right? So this is not a symmetric matrix or whatever, right? So I take this matrix and let us construct the Gershgorin circles, right? So first Gershgorin circle corresponds to the first row, second one to the second row. The first row, the center will be this entry 1 and the radius will be 1. Okay, there is only one off diagonal entry here, right? So let us just very quickly draw that. Okay, so this is the complex plane, this is the real axis, this is the imaginary axis, right? So I want to draw a circle with center as 1. Okay, so that is, let's say, center here. Let's say this is my 1 and radius as 1. Okay, so that's going to be something like this. Okay, perfect. So this is going to be the first Gershgorin circle corresponding to row 1. Okay, the second Gershgorin circle that corresponds to row 2 will have a center of 2, the diagonal entry 2, and the radius will again be absolute value of minus 1, that is 1. Okay, so it will have a center of 2 and a radius of 1. So okay, so let's just mark the points here. So this is going to be 1, this is going to be 2. Okay, so the second circle is going to be something like this. Just redraw that. Okay, perfect. So this is going to be the second Gershgorin circle. Okay, so here A11 equal to 1, A22 equal to 2, these are the centers, and the radii are R1 equal to 1 and R2 equal to 1. Both the radii are 1. Okay, that's what it's going to be. So what this circle theorem says is that all the eigenvalues of A are going to be in this region only, within this region only. Okay, you will not have an eigenvalue here, for example. Okay, this already in fact answers a lot of the questions for you. For example, it tells you that there's no eigenvalue beyond this point, right? This point is 3. There's no eigenvalue beyond 3. In fact, all the eigenvalues will have an absolute value that's less than 3. Okay, so immediately you know that the spectral radius of the matrix is going to be less than 3. You can make that conclusion right away. Okay, you can also say, for example, that all the eigenvalues have a positive real part. Okay, none of the eigenvalues have a negative real part. All of them lie in the right half of the complex plane, right? There is no negative real part. This is the real axis, right? There is no negative real part. So all eigenvalues have, positive real part. Okay, and even if there is an imaginary part, the imaginary part is at most 1 in magnitude. Okay, so you already do have a lot of information about the eigenvalues just coming from drawing these circles. Okay, of course, being a 2 cross 2 matrix and all, we can actually find out what the eigenvalues are. So let's go ahead and do that. Well, what is the characteristic polynomial, right? So here the characteristic polynomial is going to be lambda square minus 3 lambda plus 3, I think, equal to 0, right? Because the trace is 3, that's this coefficient over here, and the determinant is going to be 2 plus 1 3. So this is going to be the determinant. Okay, you can correct me later if I'm wrong. I haven't done this. So lambda square minus 3 lambda plus 3 equal to 0. That will be the characteristic polynomial, and that means the eigenvalues are going to be like what, 3 plus or minus square root of b square minus 4ac, right? So 3 square minus 12, so that's minus 3 by 2. Okay, so that's like 3 plus or minus square root 3 by 2i. These are going to be your eigenvalues. Okay, and in fact if you plot them here, so 3 by 2, sorry, 3 by 2 plus or minus square root 3 by 2. If you plot them on the complex plane, you'll actually see that these two are precisely your eigenvalues. Okay, so you can see that the eigenvalues are actually lying. In fact, in this case, they are lying on the boundary of this region. Okay, in general, they may not be in the boundary; they may be inside also. Okay, eigenvalues may be inside the Gershgorin circles also. Okay, they cannot. So it cannot be that there is an eigenvalue that's outside all the Gershgorin circles. That's the main point of this theorem. Okay, fine. So let's actually go through very quickly the proof of this. So actually the proof is not very difficult in the sense that it uses simple tools, basic definition and some basic inequalities, triangle inequality basically, right? That's all it uses. So we'll run through the proof quickly and then we'll look at some applications of this theorem. Okay, fine, very good. So let us try to look at the proof. So for the proof, we'll start with the definition. So if x is an eigenvalue, then you have ax equal to lambda x, correct? That's the definition where x is a non-zero vector. Okay, x is a non-zero vector. Okay, so x here is going to be like, an n cross 1 vector. A is n cross n, so x is n cross 1. So as usual, let me assume the entries are x1 to xn. Okay, so on the right side you must have lambda x1, lambda x2, so on to lambda xn. And this matrix A is of course a square matrix like A11, A12 and so on. I will not write down all the entries, but you can see it. Okay, so what we'll do now is we'll just expand this into a set of equations. So let's just write down the first row dot product with this vector, that will give me this entry in general. So let me just write down the ith row. Okay, so the ith row will give me A I1 x1 plus A I2 x2 plus so on A I n xn to be equal to lambda xi. Okay, that's what will happen if I take the ith row dot product with this vector and equate it to the ith row here. Okay, that's what you will get. Okay, well, compactly you can of course write it as summation xi aij xj j equal to 1 to n equal to lambda xi. That's what this is. Okay, right. Now in order to get the the center and radius kind of a description, let me try to isolate the center from these expressions, right? The coefficients are ai1, ai2, ain. Somewhere in between you will have aii, right? Somewhere you will have aii xi, is it not? Right? That will be one of the terms in this, right? And ai being the center, let me try to isolate this term and move this term over to the right hand side. Okay, so what I'll get is summation aij xj. Okay, the summation is taken from all columns except the ith column. Okay, this will give us the radius term, the off diagonal entries, is equal to lambda minus aii times xi. Okay, that's what you will get, is it not? Okay, so now we're not completely done yet. So this is actually very nice form, right? So here you have your eigenvalue minus the center. This is the form you want, right? What do you actually want to show? You want to show that lambda minus the center absolute value is less than or equal to the radius ri. That's what I want to show, right? That is the form that I will try to get it into. Okay, so this is the idea, right? I hope this is up to here it's clear. Now what I'll do is I'll take absolute values on both sides. Okay, why do you take absolute values? Remember, both left and right side here are potentially complex numbers, right? So we need the distance concept, right? For circles, we'll just take absolute values on both sides. So when you do that, you will get lambda minus aii absolute value times xi. That will be one side. I've just swapped it. I'm writing this part here. Okay. And on the right side, you'll have absolute value summation aij xj, of course, j equal to 1 to n, j not equal to I. So what I'll do is here I'll apply the triangle inequality. Right here I'll apply the triangle inequality. So that will give me summation of aij xj. Okay, j equal to 1 to n, j not equal to I. So what does the triangle inequality say? When you have a bunch of complex numbers, when you add them and take the absolute value, you are going to get something that is smaller than adding the absolute values themselves. Okay, that is the triangle inequality. That's what I applied here. Okay, so this is triangle inequality. Okay, that's all I applied. Okay, fine. So we're not done yet. So this can be done for each row. Okay, so this can be done for row I equal to 1, 2, 3 up to n. So you can write n such inequalities. Okay, remember, what do I want? I want this one. Okay, this is what I want. This is what I want to show in some sense, right? Okay, so that's what we'll try to get. So here the extra terms that you have are these x's. These x's are the coordinates in the corresponding eigenvector basically. Okay, fine. So to get rid of these x's, what I'll do is, of all these n equations, I'll consider the equation, right, corresponding to the I for which xi is the largest. Okay, so let me just write it down, it will be clear, right? Let I star be the index row, say row index, for which xi star is the largest. Okay, that means it's greater than or equal to xi for any I. Okay, meaning that you basically look at this eigenvector x1, x2 to xn and you simply pick the coordinate that has the largest absolute value. That is what you call I star. Okay, in this vector you pick the coordinate that has the largest absolute value. That's your I star. Okay, so that's basically what I have written. What is the advantage of doing that? The advantage of doing that is that when I actually take this term over to this side, right, what you're going to have is the absolute value of some coordinate in the eigenvector divided by the largest coordinate, or the the coordinate with the largest absolute value. So that's always going to be less than or equal to 1. Okay, so if I do this, then I get lambda minus a I star. Okay, less than or equal to summation a I star j, okay, xj by xi star. So what I have done here is, in this equation I have moved this term over to this side. Okay, and I'm only considering equation for that particular row, I star row that you picked. Okay, fine. Now this quantity over here by definition is smaller than or equal to 1. So you can see that this whole term here is going to be at most 1 by definition, because that is the I star that I pick. Correct? So sum here is from j equal to 1 to n, j not equal to I as usual. Okay, so that what that tells you is lambda minus a I star is less than or equal to Ri star. Okay, what you are left with here, if this quantity is less than or equal to 1, right, I can simply say this whole thing is less than or equal to summation of absolute value of a I star j equal to 1 to n, j not equal to I. This is the sum of the absolute values of the off diagonal entries in row I star, which is precisely the definition of Ri star. Okay, so this is what you will get. So what it tells you that lambda lies in I starth Gershgorin circle. Okay, lambda lies on this particular Gershgorin circle. That's what it tells you, right? So lies, I should say lies in. That's probably a better way to say it. Lies in. Okay, because you do have a less than or equal to here, right? Lies in that circle. Okay, is that clear? This is clear to everybody, right? So this equation actually means the distance of lambda from the center, that is ai star, is less than or equal to the radius. That means it has to be inside the circle or on the boundary, because it's less than or equal to here. Okay, so that's a proof. That's all. It's extremely simple and straightforward. So what does the proof basically tell you? Tells you that lambda lies in one of the Gershgorin circles. Okay, which Gershgorin circle lies on? It depends on the corresponding eigenvector. Okay, it depends on the corresponding eigenvector. So if your eigenvector has some largest element, right, then it will lie in that corresponding Gershgorin circle. Okay, but as we discussed in probably the third lecture or so, finding eigenvectors is probably a bit hard. So you don't want to avoid that. The way the statement is stated here, the theorem is stated here, it makes no reference to the eigenvectors or anything like that, right? It just says you construct the Gershgorin circles and your eigenvalues will lie inside those circles. Okay, so that is the statement of the Gershgorin circle theorem. So in the next part I will discuss some applications.